For undergrads, alpha chemistry is probably one of the harder units behind aromatic reactions. Now, in this chapter, we're looking at alpha chemistry, which is reactions at the alpha position from ketones. Now, this will include aldol reactions, Claisen reactions. This will involve alkylation reactions, conjugate addition, and some other niche ones like Stork-enamine and Robinson's annulation. We're going to look at, first in this video, at enolate formation. So without further ado, let's get into it. Our discussion must first go to alpha, beta, and gamma carbon discussion, because when you hear the idea of alpha chemistry, you need to think of alpha carbon. Now, the alpha carbons are the ones that are directly one carbon away from where that C double bond O is located. Now that would be here and here. So these two carbons. There is also something called the beta carbon, which is another carbon out, or two carbons from the carbonyl. And then we have gamma, which is 3 away. And in the future, you might learn reactions that could happen at the beta. You'll even learn one in this chapter called the Michael reaction, where we take an alpha beta unsaturated ketone and we add something to the beta position. But that's not going to be what we talk about today. That's a little bit down the road. But our chapter is going to involve chemistry that happens at these carbons most prominently. All right, that's why it's called alpha chemistry. Alrighty, so we've identified the alpha carbon. Now we need to talk about enols and enolates. You may have learned about enols, but you haven't really discussed it in depth. Now, enols, we've learned in alkynes, right? We hydrate an alkyne, it might make an enol. Let's draw what an enol is. So we have a ketone, and we have an enol. There's this idea called tautomerization, where it will flip in between these two. Usually the ketone is the major product, like 99.9%, where this is a very, very niche product. Okay, so this is roughly 0.01%, where this is 99.9%. Like, the difference is very minor, but it still happens and is very important. Now, we make enols through ketones by a catalytic amount of acid or base. So if you have a mixture of a ketone in a reaction vessel, you're going to have contaminants of base and acid, and no matter what you do, you're always going to have this tautomerization happens. Even if you have the cleanest flask in the world, if there is one atom of acid or base, you're going to get tautomerization to an appreciable amount. Now, how this happens is, I'll show you both mechanisms. Let's do the acid catalyzed mechanism. It's a little easier. Basically what happens is it says, okay, I'm going to take acid, so H plus, any H plus ion. Let's say it's from H3O plus. Alrighty. So what's going to happen is our ketone's going to steal a hydrogen. He's going to say, okay, I want your hydrogen. And then he realizes he messed up and he's like, oh no, I have a positive charge. Whatever will I do? Well, that's where water comes in to the alpha carbon and is going to say, oh, I'll see your hydrogen. I'll take one right back, but I won't take that one. I'll take this one. And we'll make an enol. So notice here we got an enol in 2 steps from an acid. Now notice how I said even if you have one atom of acid, you're still going to get it. Notice here. The acid gives a proton, and then it immediately steals a proton right back. So we just kind of swap the location of that proton. Alrighty, so let's look at the base catalyzed mechanism for making enols. Now this one's a little different, and this is where you form what's called an enolate. Now enolates are going to be very, very, very important in this chapter. They are going to be the driver of these mechanisms. Aldol condensations, Claisen condensations, alkylation. All of these reactions use bases to get what's called an enolate. Remember, a carboxylic acid, we stripped off the proton on the OH part of the carboxylic acid. We call it a carboxylate. So we have the same kind of nomenclature there, enol, enolate, okay? Basically what happens is the base isn't going to protonate and activate the carbonyl. It's just going to go right for the throat and it's going to attack this hydrogen, kick up electrons, and what we're going to notice that we get is a deprotonated enol. Okay, I want you to notice something very important here. If we use NaOH here, we'll also get a side reaction that's competing. Now, because you probably learned this in the aldehydes and ketones chapter of your course, is that with NaOH, it's going to form hydrates. Okay, so you're going to get this. Do you remember this reaction? This is true. I don't want you to forget that this is also happening. But remember, the equilibrium is going to take it right back for the more complex ketones we're going to be working with. Now, for acetone, this might happen to a very small amount, but you just need to keep in mind that there are two competing reactions in reality, but we're just describing two different chemistries that are occurring. This is on the carbonyl itself, carbonyl direct chemistry. This is alpha chemistry, which is a different reaction, but it still occurs and is important. Alrighty? I just wanted to make that point very, very, very clear. Now, remember, this is also reversible if water comes back and the carbonyl pushes out this group and goes right back. But remember, it's an equilibrium process. It's going back and forth. So with acids, with ketones, we make what's called an enol. But with bases, we make an enolate. So that's very, very, very important for you to understand. It's going to be the main pillar. It's the support of this entire chapter is the enolate. There are two notes I want to make here. Now that is unsymmetrical enolate formation, and we're also going to talk about, let's say you use a reagent known as sodium hydride. So let's start with our first idea here. Now, if I have an unsymmetrical ketone and I ask you, what is the base going to attack? I first have one option up here, which is a strong base, and then I have a second option here, which is a strong, bulky base. What do you think is going to happen? Remember, when we form a pi bond through some sort of elimination process, which is actually what this is, it's alpha elimination. That happens to kick up electrons there. This is going to follow that rule that says if you have a bulky base, attack the less substituted side because of steric interactions. But if you have just a strong normal base that's not that bulky, attack the more substituted side. Make the more substituted alkene. That's exactly what actually happens here. If we have a base attack this, that's just normal, it's going to make the more substituted alkene to form an enolate. Okay, what if we use bulky though? Well, the bulky fat bases like DBU, DBN, LDA, terbutoxide, or like that would have to be sodium terbutoxide, right? These kind of bulkier, bigger bases. Also, LDA you've probably never seen before, lithium diisopropylamine. That will come up in alkylation. Oh, little sneak peek. Anyways, these bulky bases, they're not going to want to go here because they're just going to get repelled by all that steric interactions. They're going to attack here where it can just kind of sneak in and steal a proton really easy. So what happens here is we get a different enolate where it's on the primary side or a terminal alkene. Okay, so this should be an important idea that's going through your head when you're going through these reactions, thinking to yourself, okay, I want to do a nice little reaction synthesis problem here, but it seems like I'm getting a very, very weird product. How can I do that? If you have this idea in your head going through the rest of this chapter, it will help you greatly. Next, I want to talk about using sodium hydride. Now, this is irreducible enolate formation. Basically, what this says is I'm going to make hydrogen gas. And what does a gas do? Take a flask, do some reaction producing gas, it's going to bubble out. Okay? And you're going to be left with whatever you have left here. So remember, if we used sodium hydroxide, for example, the conjugate base, water, could just come back in and reverse this process and make our ketone again. We do not want that. We want it to go to make the enolate indefinitely. So what happens is we use sodium hydride, where sodium has a positive charge, hydrogen has a negative charge, and what it's going to do is it's going to attack the hydrogen, not the alpha position, and form an enolate. It's going to form our enolate and form hydrogen gas. Now look at this. Well, if the hydrogen gas escapes, can the enolate attack the hydrogen gas? Well, you'd say no, that's impossible because the hydrogen gas ain't in the same volume as this one. All right, so hopefully that idea makes sense. This is very important. If you are in, like, say, grad school or something and doing these reactions or devising these syntheses and you're having a hard time keeping that enolate and it just wants to go back and do a ketone, use sodium hydride. It will get you to the end process where you make hydrogen gas. Now, this reaction is a little bit scary because hydrogen gas is very flammable. If you light it with a match, it just explodes. And if it's all in your laboratory, you have a spark, that will blow up, and it's kind of dangerous. So it's kind of rare to see this idea, but it is irreversible, and it is a very, very good idea. Alrighty, so that's going to wrap up this section. This was just on the alpha carbon and the enolate formation. Next, we're going to be looking at how we can halogenate using alpha chemistry, putting halogens in the alpha position. This is also known as alpha halogenation.